Today is the 25th. I have to say, linear algebra is one of my favorite things, favorite fields in mathematics. And it's pretty much up there with 241 probability. I remember I heard a professor once when I was at Michigan. He said, these are the two main mathematics that one should know. Yeah, I hope it's contagious too. Uh, Linear algebra and probability are two major subjects in mathematics, branches in mathematics that is becoming ever more present and relevant in our world. You guys heard of machine learning, linear algebra, but you also need a little bit of probability to understand some of the things that, well, you definitely need probability to understand machine learning because there's a lot of probability in those algorithms and in analyzing how good of a performance your algorithms are performing. So if I could I think someone else who was in the other class have heard me say that if I could, I would change a bit of the curriculum for high schoolers so they can learn probability earlier. And not just that, I hope that we can make linear algebra more of a thing where it's not just for advanced students, but something that we can build up. Because as you all start to see, linear algebra is becoming more prevalent in our world. Are we going to have a lot of statements which we have to remember? Oh, let me tell you this. Yes, of course. Of course. This is a 4-credit course. It's 2 hours every time. There's going to be a lot of stuff. Believe me, it's going to be a lot of stuff. So what is linear algebra? How do we begin this story? Let's head back a bit in time. So before we even do anything, let's break down this a bit. What in the world is linear? What does it mean? What does that mean? Linear. What is linear? Mx plus b. Right. Y equals mx plus b, right? That's what you think of when you think of lines. You think of a line. But the thing is, that is a bit of a narrow definition of linear because you're dealing with something that's only in a 2-dimensional space. So linear can be extended. The idea of something being linear can be extended to more than 2-dimensional space, to 3-dimensional space, 4-dimensional space, so on and so forth. So that's where the word space comes into play. Vector spaces, right? You guys have learned about vector spaces, but they never said that you've learned vector space. So we're gonna save that though for a little bit later. I don't want to like lose you guys already with the terminology of vector spaces. But let's stick with the 2x2 example, right? So we're all very hopefully knowledgeable of the Cartesian plane, right? Also known as the XY plane. The Cartesian plane, the rectangular coordinate system, the XY plane, right? We have been seeing these lines being drawn for years, hopefully. And somewhere along the lines around in Algebra 1, whether it be in high school or if you took college algebra in Queens College or somewhere else, community college, or wherever you took algebra, you've learned about systems of equations, right? And in particular, there's different kinds of equations, but the kinds that we've talked about, or you've probably seen, are systems of linear equations, right? And again, the word linear implies y equals mx plus b. We have lines, just random lines, right? 2 lines, right? So what kind of lines have we seen? Well, we've seen the kinds where we have one solution, haven't we? That's normally what we want. One solution. What does that one solution look like? We have two lines. Draw a little bit angled. We have these two lines and they intersect at a particular point. And that particular point is called not just a point of intersection, but this is actually called the solution of the system. It solves the system. And what that means is it makes the equations true. Right? One solution is one point of intersection. What we call these systems being consistent. So that's one thing we call it, consistent. Consistent system. So this is like one kind, right? One type. But of course, what else can happen? Do you guys know? What else can happen when we have two lines randomly drawn?
They don't necessarily have to meet, so there would be no solution.
Right. So we can have situations where they don't meet. Now, do you know the condition as to
They
when?
have to be parallel lines.
That's right. So we have situations where we have two lines drawn and they are parallel, right? So let me just write these as bullet points. So we have situations where we have two parallel lines. If you have parallel lines, you have the same slope. And there's no point of intersection. So there's no point of intersection. Oops. Which means there's no solution. So we have situations where we have no points of intersection, so henceforth no solution, right? And we call this an inconsistent system. Okay, and is there any other situations that arise with linear system of linear equations? So we have situations where we have one point of intersection. We have situations where we have no
I'm
point of
sorry.
intersection.
It could also like they're the same lines, so like on top of each other.
Yeah, that's like one of those weird situations, right? Hold on. So those are very strange situations where we have the same line. So it's kind of like having one green line and then the same line on top of it. It's one of those things like it's kind of hard to do that.
Yeah,
But the idea is you see the idea. The idea is that you have one equation on top of the other. So if you have one equation on top of the other, how many times does it intersect?
it's infinite many times.
Right. So we have two same lines. So the lines are identical. And then we have infinitely many solutions. So these are the three kinds of systems of equations that you may most likely have seen before. And we're dealing with a 2x2. When I say 2x2, I mean two variables and two equations. So these are the kind of systems that you've seen before. So you have been familiar with, you have most likely seen systems of equations, I should say systems of linear equations with two variables and two equations. If you have an equation and you have two variables, you can't solve it because you need two equations along with those two variables in order to solve. So let me give you an example. So this is an example of a 2x2 system. We call it 2x2 because there's a 2x2 system. And we'll be utilizing this kind of phrasing a lot more when you start to see more variables and more equations. But we've seen this before, right? And how do you solve this? How would I solve? Do you guys know how to solve system of equations? How do we solve it? Okay, we can do several things. There's three ways. One thing we could do, solve for one variable for, right. Okay, so you guys have seen this. So one way to do it though is graphing, right? These are two lines, right? So we can graph each and then see where they intersect. That's one way. The other way is substitution, where you solve for one variable and then you find it in terms of the other. Or you can do elimination. So which one should we do? Or can anyone guess? Or can anyone see what it is or what it would be? It's a simple one on purpose.
Elimination.
Elimination, but can you solve what the system is? Like without doing anything? Would you be able to tell what X and Y would be? Jatanya raise his hand.
I think, Professor, we can multiply the first equation by 2 or maybe 3.
No, but I'm asking, does anybody know what the solution is without even doing anything?
Oh,
No, does anyone see it? ZU. Yep. 1, 2. Does that make sense?
Mhm.
The solution is 1, 2, where this is the X coordinate and this is the Y coordinate. And then we can check, right? How do we check? Well, look at the first equation. Look at the second equation. In the first equation, equation 1, what do we have? 1 plus 2, doesn't that equal 3? It sure does. And then how about the second equation? 2 times 1 plus 3 times 2. Doesn't that equal 8? Because 2 plus 6 equals 8. So you see, this is the correct solution. So I can find the solution if the numbers are easy enough. I can find it. Now, let's use one of these methods of solving. And let's use elimination because we're going to be using elimination a lot more. So again, this is just to get our feet wet, just to get used to what's going on. Get ourselves familiar with what kind of territory, what kind of terrain we're going to be in. So x plus y, right? So we got x plus y equals 3, and we got 2x plus 3y equals 8. And then someone says, hey, we can just multiply the first equation, multiply it by -2, for example. Because when we multiply by -2, the first equation is -2x minus 2y equals -6. And then we get 2x plus 3y equals 8. We didn't touch the second equation. And then what do we do after that? We add. And why do we add? Well, the reason why we multiply the first equation by -2 was so that we can eliminate the x values, the x variables. Because we have -2x in the first equation, we got 2x in the second equation. So when you add them up, you eliminate x. So I eliminate x. And what's nice about that is that when I eliminate x, I'm only left with y. And -2y plus 3y is positive y. -6 plus 8 is 2. And guess what we just found? We found y equals 2. And then I can find what x is by using one of the original equations. So if we look at the first, so I'm going to call this equation 1, equation 2. So in equation 1, we got x plus y equals 3, but we know y is 2. So x plus 2 equals 3. So that means that x equals 1. So here we have a solution, which we already knew, but we found it we used elimination. So is everyone comfortable with this? Has everyone seen this before? Nothing new, right? Everything good? Okay. So yes, you must have seen this before in algebra. Now, what's so hard about this, you may ask, right? Like it's just a 2x2 system. We can just use elimination all the time, or substitution, or graph. The problem is when we have higher level, we have more variables and we have more equations. Then this procedure, elimination, the way we have it here, becomes very cumbersome. And that immediately happens the moment we have 3 variables and 3 unknowns. The moment that happens already, we're at a disadvantage. And let's see that now. So let's look at 3x3 systems. Now, before we head into this, what does it mean to be linear in a 3-dimensional space? So in a 2-dimensional space, right, as we have seen, a line or a linear object, if you will, a linear object is considered a straight line in 2-dimensional space. But the moment we're in 3-dimensional space, what does that become? Or how do we visualize that? How do we interpret something being linear in 3-dimensional space? So this is when we have the x and y axis, right? This is the z axis. So then you should probably get some flashbacks for those of you who took multivariable. 3 lines meet at a point. So this is when things start to get a little bit interesting, right? Because in the 2-dimensional space, there's only 3 scenarios. But now we're talking about 3-dimensional space, things can get, there's a lot more variation. And Saida says 3 lines meet at a point. So you're not necessarily wrong, but it's a bit inaccurate to say lines. So now we should talk about being linear in the 3-dimensional space. So let me just say what linear is. Linear in a 2-dimensional space, right? I know you guys are used to lines being y equals mx plus b, but there's another form of a line that we use a lot more. This is called the standard form. And maybe you've probably seen it, maybe you haven't, but it's not so much utilized unless you talk about systems of equations. And that's, you've probably seen this, ax plus by equals c. Have you guys seen this before? And you see most of our when you talk about solving systems of equations, we most of the time, our lines are presented in this fashion, right? They're presented as ax plus by, where a and b's are coefficients, x and y's are the so a and b are coefficients. Most of the time are real coefficients. C is usually a constant of some sort. And x and y are the variables, right? That's what you have been used to all this time. And now what does it mean to be linear in a three-dimensional space? We extend the standard form of a line to three-dimensional space. So when we do that, right, now we're including the z variable. So all that's happening is we're doing the same exact thing. We're doing ax plus by plus cz, if you will, equals d. Now, what does this represent? Does anybody know what this geometrically looks like in three-dimensional space? What is ax plus by plus cz equals d? Where a, b, and c are all, a, b, c, and d are coefficients. And x, y, z are variables. Does anybody know? What does this represent? ax plus by plus cz equals d. Thank you, Mir. Yes, Mayer. It's a plane. Do you guys remember planes? It's basically like taking a loose leaf paper and just making that an infinite plane, like infinitely expanding a loose leaf paper in our three-dimensional world. It's kind of hard to draw that. So you can think of it like a sheet of paper in three-dimensional world that goes on forever. Okay, so that's what we're dealing with in a 3x3 system. We're going to be dealing with three planes. Do you guys understand? In a two-dimensional system, right, we're dealing with two lines. They intersect, they don't, or they're the same thing, right? In three-dimensional space, and hopefully it's hard to do this in a two-dimensional space plane that we have here, but think about having planes and having three of them. And there's different variations of that occurring. Actually, I won't be able to do this by hand, so I might as well. Hold on, guys, give me 1 second. So, if you guys see it, I took a photo of what I mean, because I'm not gonna be able to do this by hand. So even this is not probably the best representation, but you see, these are all planes, and these are all the scenarios that could occur when you have three planes in space. You can have all of them being parallel, there's no solution. You can have two of them being parallel, but one of them not being parallel. Do you see how the intersection points are two lines? Like this would be the intersection point here, lines and lines. But there's no solution, meaning that there's no XYZ coordinate that solves all three. You have this scenario here where they're all kind of like they're intersecting one another, but there's only intersection of two planes together, not all three. And so the only way this occurs, or the only way for a solution to exist, is if they all intersect, so that when they do intersect, there's only one point of a common point of intersection. Do you guys see that? So Sam, you said, so the point of intersection would be a line. Well, the thing is, it could be a line, but as you can tell, right? For example, this scenario here, you have two planes that are parallel to one another, and there's one plane that cuts through them. This upper plane here intersects with this diagonal plane, and it represents a line. It does represent a line. But all these points only satisfy those two planes. It doesn't satisfy the other plane. So henceforth, there's no solution. Do you guys understand? So the idea is that when you solve a three-dimensional or 3x3 system, what you're finding is what you want to find, if it exists, is a single point where they all intersect. And that single point is your solution. And that point solves or satisfies every equation that you have in your system. What I'm trying to show you guys is it already becomes complicated the moment you go from 2x2 system to a 3x3 system. And it becomes even, we can't even interpret it when we talk about 4-dimensional space, 10-dimensional space. And then when we talk about like all these machine learning algorithms that deal with 100-dimensional spaces, or even beyond that, 100,000 dimensional spaces. So where is the point on the solution? So Xavier says, where is the point on the one solution? The one point here, I know it's kind of hard to see that, but it's this point right here. Do you see that? So we have one plane here, we have another plane here, and then there's another plane that cuts through. And then that point where they all meet, that's your solution. And I think Baldwin, you have a question?
Yeah, I'm just having trouble understanding that one next to the one solution, the infinite many solution.
Yeah.
How is it many if they're like at an angle and this one cuts? If that makes sense.
They're infinitely many because they're, how can I say it? They're cutting in a way where their point of intersection is a straight line.
Oh, so they don't, okay, so it kind of like in the
Yeah, I know
middle.
it is hard. Like, I don't know how to use, like, should I use my hands? So like you have a plane, you have another plane that cuts, right? That cuts
Okay, I
through.
understand. Uh-huh.
It's a straight line that's cutting through these two planes.
Oh,
Get another hand, I don't know, another plane,
yeah,
and
and
then
then, okay, no,
goes right
I
through
get
the
it.
same line. So that has
Gotcha.
infinitely many solutions because the intersection for all three planes is the same exact line.
Understood.
But do you understand? But the
Yeah,
idea, yeah, yes. So because the line has infinite points, it has an infinite number of solutions. So what I'm trying to tell you guys is it already becomes complicated the moment we step into three-dimensional space. Just understanding it geometrically. And then beyond that, it's we kind of let it go. We kind of let the whole geometry aspect of it, we just let it go. And then we just start concerning ourselves with solving the equations. So we're dealing with the numbers, and that's where the matrix is born. Because we can't continue interpreting these higher level dimensional systems as something geometric anymore. We're just dealing with the equation aspect of it and the numerical aspect of it. And that's why the matrices are come to life. So let me see if I can show you. Anybody else have questions? Good. So an example of a three-dimensional system. So see, we have a three-dimensional system. We have three unknowns, x, y, and z, and we have three equations. First, second, and third equation. So these are three different planes in three-dimensional space. And what I'm trying to figure out, if it's possible, is if there's a point of intersection that all three planes intersect that. Now, let me ask, does anybody know how to solve this? So two-dimensional spaces, right? Two-dimensional systems, that's easy stuff, right? That's hopefully we're okay with that. Now we have a three-dimensional system. Are we okay with this? Has anyone solved this?
I know how to do it with my calculator, but I don't know how to do it.
Okay, wait. How did you do it in your calculator?
My teacher, he taught me to like take matrix A and then the inverse of matrix B, I think, and then you
Yeah.
get the solutions.
Yeah, and that's it. Wait,
I wouldn't know how to do it by hand.
in what class did you learn this?
That was like in high school. I think it was like
Oh,
geometry or something.
okay.
No, like
Okay.
algebra, something like that.
So he showed you the shortcut, and then you're like, oh wow, I can't believe I can do this.
Yeah, it's so much easier.
Right. It is so much easier. I agree. But linear algebra is literally learning why you're able to do that. Like you're gonna learn how to do it without the calculator, but eventually we will use it later. But the beginning of linear algebra is basically understanding how the calculator would, or how would you by yourself do it. Okay, so I'm going to show you just the way that they normally teach it is also by elimination, because if you notice, if you try to do it by substitution or even by graphing, already by graphing, you're like, how do you graph a plane? And how do you determine where they intersect? Like that already gets complicated. So graphing is not a great way. Substitution is not probably the best way because you have three variables to take care of. It's still doable, but not the greatest way. The best way is by elimination. So we're going to solve by elimination. Now, this takes a bit more work because you have three equations. So what we're going to do is, instead of dealing with a 3x3 system, we're going to try our best to eliminate a variable completely so that we're left with a 2x2 system. So a lot of times in mathematics, solving problems is based upon solving a simpler problem. That's usually a technique when we talk about problem solving. If you have a problem and you're like, this is a complicated problem, you try to simplify it in some way. Think about a problem that looks similar to it and see if you can solve that, and then see how you can apply that to this new one. So we know how to do 2x2 elimination. So maybe applying it here, it directly can't work, but we can try to work our way to that point where we can use only a 2x2 system. So the way that works is we take any two equations. So let's take equation 1 and equation 2 and eliminate one variable from it. So let's take equation 1 and 2. And for now, let's eliminate z. So first equation is x plus y plus 2z equals 9. And the second equation is 2x plus 4y minus 3z equals 1. I want to eliminate z. So I look at z here and I look at z here. How do I eliminate it? What should I do?
You could multiply by 3.
I can multiply the first equation by 3. And then how about the second equation?
By 2.
By 2. So when I do that, what happens? I get 3x plus 3y plus 6z equals 27. And then I get 4x plus 8y minus 6z equals 2. And then when I add these, what happens? I eliminate the z's, and I'm left with what? 7x plus 11y equals 29. So you see that I reduced the three variable, the two equations with the three variables, I reduced it to one equation with two variables. So what do you guys think the next step would be? What's the problem here? I have one equation, two unknowns. So I would need another equation with also two unknowns. So what would I do now?
Would you use equation 2 and 3 and we'll try eliminating them?
Exactly. So I would say, hey, take equation 2 and 3. I compare those up. Since I paired up 1 and 2, why not also do 2 and 3? And do the same thing, eliminate z. So then what do I have? I got 2x plus 4y minus 3z equals 1. I got 3x plus 6y minus 5z equals 0. So I want to eliminate the z's. So I have to multiply the first equation and the second equation by a certain number. And how do we determine that number? We can look at the least common multiple among the variables that we're considering, the coefficients of the variables that we're eliminating. So 3 and 5, the least common multiple is 15. So we multiply 3, and if we want, we can multiply by -5. So we can have the opposite signs, and then we multiply this by 3. When we do that, what do we get? We get -10x minus 20y plus 15z equals -5. And then the next equation would be 9x plus 18y minus 15z equals 0. Then when we add this, what happens? The z's cancel, and I'm left with -x minus 2y equals -5. And look now what I have. I got an equation with two unknowns. So now what did I just do? I broke down the 3x3 system into a system of two equations with two unknowns. And now that should be simple enough to solve because we know how to do this with our eyes closed, right? So this is my system now. Now, what do I do with this? It's elimination upon elimination upon elimination. So now here, I want to solve this. So what do? I can eliminate x or y. Sam?
Yeah, at this point though, since it's only two variables, you could use any of the three that conveniences you, right?
Correct.
Okay.
Correct. So at
Because I
this
see
point,
substitution doesn't seem too hard either.
yeah, substitution, you can solve for x for the second equation, you can solve for x. That's pretty straightforward.
Gotcha.
But from here, I would say just continue with the elimination train here. And I would multiply by 7, the second equation by 7, so that now I get 7x plus 11y equals 29. Then this becomes -7x minus 14y equals -35. Now when I add these, the 7x's cancel, and I'm left with -3y equals, and this becomes what? -6. So what does y equal? 2. So I solved for one of the variables. I did it. And then what do I have to do? Get x and z, right? So then I can use any equation that has x, has y in it, and has either x or z in it. So because I'm solving this equation here, might as well find x, right? So if I know what y is, then finding x should be straightforward. So I'm going to use the second equation. So negative x minus 2 times 2 equals negative 5. Negative x minus 4 equals negative 5. I add negative 4 on both sides. I get negative x equals negative 1, which means that x equals 1. So I was able to solve x and y. I got 1, I got 2, and then now I got to get z, right? So use the first equation or second equation or the third equation. It doesn't matter. Let's just use the first equation of the original problem. So we got x plus, what is it, y plus 2z equals 9. So you can plug in 1 plus 2 times z equals 9. I get 3 plus 2z equals 9. Whoops. I get 2z equals 6. So I get that z equals 3. Pretty straightforward, right? So then what's the solution? The solution is the coordinate in space is 1, 2, 3. So these three planes in the three-dimensional space, they all intersect at one point, and that point is 1, 2, 3, which equivalently means that if I plug in these x, y, z values into each equation that we started with, if I plug it into each of these equations, it would satisfy all three. That's what it means to be a solution. So you see, we had to do a bit more work for the 3x3 case. Not crazy amount, but it's you have to eliminate several times. And then the question becomes, what happens when you have a 4-dimensional 4x4 system? Then you're like, okay, now it's crazy. Now it becomes crazy. And this is where matrices hopefully help, and they do. They definitely do. So let's go back to the example that we started with. So now we're gonna see why we care about matrices and what's so special about them. So just like 2x2 systems, if they intersect, they only intersect at one point or infinite points. Pretty much, yeah. There's no other. There's no like 2 points, 3 points, because it's not possible. Geometrically speaking, it's not possible. That's a good point, though. Yeah. So systems only really have, when they intersect, they do it either at one point or at infinite number. There's no in between. Okay. So let's go back to the one that I said, right? Let me just copy this. So let's revisit the first 2x2 example. So we have this guy here, right? And we're like, okay, we know how to solve it. We know the solution already. It's 1, 2. Why else do I need? Why do I have to think about this again? Well, there's a way to simplify the computation as we get bigger and bigger systems. And what we introduce is called the matrix. And there's different notations for this. Some people like using like the square brackets. Some people like using the parentheses. It doesn't matter which you choose. All that matters is that you're consistent with the way you arrange the coefficients. So what we're going to be considering is, if you look at this, right, there's a bit of structure behind these systems. I don't write y first and then x. I don't switch this. I'm not writing it like I'm not writing the coefficient, the constant first, and then putting the variables here and having it there. No, I arrange them so that you have the x's in one column, the y's in the next, right? And then they both equal a number. Do you see how there's structure behind this? Even just visually speaking. So we're gonna take advantage of that. And we're gonna create a matrix based upon this structure. So we're gonna create rows and columns. It just is a natural way. It's a natural way to arrange this. And then this becomes like something similar to, like, I don't know, you guys play Battleship, where you know, like you put the coordinates, right? Like it becomes like a
Yeah.
coordinate grid. Yeah, right. You guys remember that? So it becomes like a coordinate grid. Of course, we're not going to draw this all the time, but it's just to give you a visualization of what's happening. Row 1 is associated with the first equation. Row 2 is associated with the second equation. The columns are associated with the variables. So column 1 normally is the x variable, and column 2 would be the y variable. And then you start to see how we can extend this, right? To a 3x3 system, we have 3 rows, 3 columns. It becomes very natural. So what are we going to be including in this matrix are the coefficients of the first row. So the coefficient of the first row is 1, 1 on the first equation. And then the second equation would be 2, 3. So that I created a matrix, and you see it's a 2x2 matrix. And this phrasing becomes much more common, 2x2. It's a 2x2 matrix because it's 2 rows and 2 columns. So it has a total of 4 entries. And these entries are associated with the coefficients of the first equation and the second equation. So does that make sense about matrices? Okay. So that's a matrix. We call this a matrix of coefficients, right? And what we're going to tend to do is not just, and maybe you may ask, wait, what happened with the 3 and the 8? We just let it go? So no, we're actually going to include it as well. But this is called an augmented matrix. So the augmented matrix is the matrix of coefficients, right? So we have 1, we have 1, we have 2 and 2 and 3. And what people tend to do is they draw like a vertical line, or sometimes they draw a dotted line, either or. And that dotted line, we do draw. These we don't draw. This is just for visualization of the location of the numbers. But this line is to indicate that we have an extra column. And that extra column are the coefficient, the constants that each equation is equal to. So that's where we include the 3 and the 8. Again, this is the x and the y coordinates, the x coefficients and the y coefficients, and 3, 8 is the constants. This is called an augmented matrix. Augmented, we add an additional, this is the augmented column. Okay, so far so good. Any issues with the form of a matrix, how we arrange a matrix, how we and there's nothing special. There's nothing special about having 1, 1 here. We can also have 2, 3 first. Like we can also rearrange the equations. So it's nothing special about having 1, 1 first. But as long as you are consistent with the way you write it, that's all that matters. As long as you're consistent with the variables being the first column being x, the second column being y, as long as you're consistent with that, it shouldn't matter. Okay, so now we're dealing with matrices now. And you can think of it now as a game. Now, what's my game? What's the goal of this game? The goal of this game is the numbers that you have here in this grid or matrix. I want to perform what are called elementary row operations. That sounds very complicated, but these are called elementary row operations. So you can think of them as certain moves that are legal in this game that we're playing. And what's the game that we're playing? We're trying to solve the system. That's most of our, at least up to this point, most of our objectives in mathematics is to solve equations. We want to solve things. And what that means is find what the X and Y and Z are, or what X and Y are. Like, that's what we care about. We care about the numerical solution. So you can think of them as legal moves, okay? Legal moves applied to a matrix. So the crux of the beginning of linear algebra is dealing with elementary row operations. That's how we're going to start this whole matrix concept off. And there's only 3 of them, so you don't have to worry about 3. At first, it may sound kind of like strange, these kind of operations that we can do, but then hopefully you see the connection with what you've been doing already with elimination. You've already have been doing row operations without knowing you've been doing row operations. So the first one of them is that you can multiply a row by a non-zero constant. You can do this. And if you think about it, you've done it. When you did elimination, what do you guys do? Oh, I want to multiply the first equation by 3 and the next. You understand? So you all already know this move. You just didn't know it's like a formal thing. You can multiply a row by a non-zero constant. That's legal. Okay. The second thing you can do is you can swap any row. Swap the order of the rows. Which is kind of what I touched upon here, right? I say, hey, what's so special about having this being the first equation, this being the second equation? There's nothing special. I could just switch it and have the same system, just change the rows. I can do that too. So I can swap the rows here, for example. I can swap them, no problem. It's a legal move. It's called an elementary row operation. That's the second thing. And now the third thing is very similar to the first one, is that you can add a constant. So this one is it's a little weird to write out in words. Add a constant times one row to another row. Not only do I put a star there because it's a little weird to say to write out, it's also I also put this a star here is because this is like the most utilized operation. And again, you've been doing this already. The moment you guys decide to do this, the moment you say, hey, let's multiply this row, this one here. Yeah, go to the this one. Like the moment you said, hey, let's multiply this equation by -2 and let's add it, and you eliminate the x's, that is the same thing as applying this third row operation. And I'm going to take you step by step. So we're going to take this row. We're going to take 1. We're going to take 1, 3, 2, 3, 8. Okay. So again, I'm going to write this out. So these are the row operations that I have in mind. And my goal is to solve the system. How do I know if I solved the system or not? The goal is to make this coefficient of matrices, make it where you have 1s in the diagonal and 0s everywhere else. This is the goal. The goal is to transform this matrix 1, 1, 2, 3 to 1, 0, 0, 1. So what does that mean? How do you translate that into matrix world? Well, look at the first row in the first column. It's already a 1. So I have it already. I already have that part there. I'm good with this one. You see? What's the problem though? I have a 2 in the bottom. I don't want this 2 no more. I want this 2 to become a 0. So how do I do that? I apply an elementary row operation. What I'm going to do is I'm going to use the third option. I'm going to eliminate 2 by doing what? Multiplying the first row by a number. So when I add it to the second row, it becomes a 0, which is very similar. I would say it's identical to what we did when we did elimination, right? We multiply the first row by -2 so that when we add it, the x's eliminate. Do you guys see the connection here? That's right, Mayor. You said exactly right. So what am I going to be doing? I'm going to be doing this. I'm going to be multiplying -2 to row 1. I'm going to be adding it to row 2, and this becomes my new row. So that's the way we write this out. This is a way to write out the row operation. The first row, I'm multiplying the whole first row by -2. I'm adding it to row 2, and I'm making that my new row. So it's very algorithmic in nature. So I'm not changing the first row. I am not changing the first row. I'm just using it. So when I multiply it, so you kind of have to do it in your head a little bit. If not, I can write it out. So what happens to the first row? The first row is -2, -2, -6, right? That's the first row. And the second row is what? 2, 3, 8. And what happens? I add them, right? When I add these up, what happens? I get 1, 1, 2. So that becomes my new row. This is my new row. 1, 1, 2. Do you guys see what we just did? I applied the row operation.
Is a 0 on the second row. 0, 1, 2.
Say that again.
The second row.
Oh, that's right. What am I talking about? I can't even add. Can you believe that? Can you believe that, guys? I can't even add. -2 plus 2 is 0. You're right. That's exactly what I wanted to do. Thank you. Yeah, Xavier said the same thing. That's exactly what I wanted to do, right? I wanted to make this 2 no longer a 2. I wanted to make it a 0. So you see how this first column here is taken care of? Check. Now, what's the only thing that I need? This here looks very much like this, except for what? This entry up here, this 1. So I want to get rid of that. So Chaitanya says, now what do we do? The next row operation would be what? I want to eliminate this 1 I want to make it a 0. What do I have to do? I have to take row 2, multiply it by -1, add it to row 1, and make that my new row. So then what does that look like? So the second row, right? This is row 2, negative row 2. The second row looks like what? 0, -1, -2. Then this is row 1. What's row 1? 1, 1, 3. When you add these up, what happens? You get 1 still, you get 0, and then you get 1. So my new matrix looks like this: 1, 0, 0, 1. This is 2, and this is 1. You guys see what we just did? We essentially performed elimination. But now we're only dealing with the numbers. We're not worrying about the X and the Y and the Z. We're just dealing with the numbers now. And again, what has not changed? The columns here represent X and Y's. And then if you read it off, what does this first row tell me? It tells me that X equals 1. And it tells me that Y equals 2, which is exactly our solution. You get to 2 points. Yes.
I got one question. So for the negative R2 plus R1, can I just say like R2 minus R1 then become the new R1?
You
Because
said R.
can I not doing like -1 like -1 times row 2 first, or can I just do like R2 minus R1 directly?
R2 minus R1. The thing is, if you do R2.
Yeah, instead of a negative R2 plus R1.
Oh, you're talking about like just rearranging, like saying this R1 minus R2 like this?
No, R2 minus R1. Can I do that? Then becomes
I think you come out with a
R1.
different number, right?
I'm sorry.
I think you come out with a different row. You can do it. You can do one more step though after that. Like if you do this, right? You're saying R2 minus R1, right? And make that R1. Is that what you're saying?
Yes.
So what is R1? What is R2, I would say? R2 is what? 0, 1, 2, right? And what is negative R1? A -1, -1, -3.
Oh, I'm sorry.
When you add, you get -1, 0, -1, right? So you get this. You get this,
Oh, yes.
which is okay, right? But then
Yeah.
you have to apply one more rule. You have to multiply everything by -1 so that the negatives go away. You see that? Because
Oh,
at the end of the day, the game is to get this matrix to look like what? 1, 0, 0, 1. Which is essentially saying find X and find Y, which we did.
okay.
Now, it may not be that impressive because it's a 2x2 system. But the idea is, guys, that this becomes very useful when you have a much larger system. And then it gets more complicated. And there's a lot of algorithmic nature of it. Like there's a whole world about this called numerical linear algebra, which is associated with numerical analysis, which talks about how effective certain algorithms are in performing this kind of elimination. And this is called Gaussian, it's called Jordan Gaussian elimination. So we'll talk about this more next time. But Baldwin, yes, you have a question.
Just going back to the structure that you were talking about earlier. So for example, each row would be dedicated for one variable. For example, the first row would be for X, the second row would be
Second, no, okay, be careful, be careful. The words row and columns has to be clear. Row is horizontal and row represents an equation. The columns are representing the variables.
Okay, so what I meant is, so the first column, for example, would be for the letter X, but
Yes.
then the row would be for the
First equation.
for the answer for the variable X.
Oh, you're talking about like at the last
Yeah, like at the last step, like
at the last thing, right? We want the first entry to be 1.
Mhm.
And because we started with X being that first column, then that represents the X variable.
okay.
So if you read this off, this first row, this is saying X plus 0y equals 1, which just means X equals 1. And the
Okay.
second row, if you read it off, is 0 times X plus 1 times Y equals 2, which just means Y equals 2.
Right. So this is like what the calculator is doing in the background, right?
You can say that, yes.
Hmm.
And then eventually, this application, right? We apply it to what I wanted to do, but didn't have time. Is the 3x3 case. It's the same game. So let me just do that real quick. It's the same game. I'm not gonna do the whole thing. I just want you to see what the matrix will look like. It will look like 1, 1, 2, right? 9, 2, 4, -3, 1, and then 3, 6, -5, 0. That's going to be my augmented matrix. And now what's the goal of this game? The goal of here is to make this look like 1, 0, 0, 0, 1, 0, 0, 0, 1. So the idea is take this first, this is already a 1. Now eliminate 2. We already know how to do that because we did that just now. And then after we eliminate this 2 to become a 0, make this 3 a 0. Do the same thing. And then just rinse and repeat. Make this middle number now a 1. And then so on and so forth. Get rid of this. Make this a 1. And then go backwards. Get rid of these, get rid of these. And when you apply all those elementary row operations, you're going to get x. Right? You can get 1, 1, 1. Everything else zeros. And you're going to have the solution on the right. So that's the idea.
Okay, makes sense.
And then you just keep on going as things get bigger and bigger. All right, so I'm gonna stop